All right, let's go ahead and get moving. So on this first one, we want to try and solve this. We want to get all the way down to an x equals. What are we going to need to do? We need the bases to be the same. 3 to the power of minus 1 whenever we have these kinds of fractions. I can rewrite this as 3 to the x plus 9 equals 3 to the minus 1. Once we get those bases the same, now we can set the exponents equal so we can solve. Yes, we started when we were working with these kinds of things on Friday.
Did we leave off with story problems?
Yes, we have 2 more story problems we're going to do. Yes. I have a couple more copies of it if we need it. So what do we get? What is our solution for x? Minus 10, negative 10. Minus 9 from both sides. Get up and get a marker. It's fine. They're there to use. Okay. So this one was a pretty simple one, kind of warming us up, getting us back in the zone on these. We need our bases to be the same so we can use our exponent laws to solve stuff. Because sometimes we get grosser looking stuff. We'll get something like this. E to the minus x squared equals e to the x to the second times 1 over e cubed. Ew. Well, the left side is actually just down to 1 single e, so this left side I don't need to do much to. But I do need to adjust this right side a bunch because in order for me to set my exponents equal to each other, I can't have more than one term. I need to have one base to a power. So I'm going to need to do some simplifying over here. When I have powers to powers, what can we do with those? Multiply them. So this is the same thing as having e to the x times 2 or e to the 2x. And then we just did one very much like this where we had a fraction. So this is the same thing as being e to the minus 3. Well, now I have everything as powers of e, but I need to get down to just one single e on the right-hand side. So what can I do with my exponents when I multiply my bases? I need to add those exponents. So this is the exact same thing as if we had, I'm going to skip a line here just so we have space, e to the minus x squared equals e to the 2x plus negative 3 or 2x minus 3. When our bases are the same, we add the exponents. If we have powers raised to powers, we multiply those exponents. So we're busting out some of our old school algebra power rules, exponent laws. Once we get it down to one exponent on each side, now I can work on solving this, being able to ditch the e's. Once we get those bases the same, I really care about when does minus x squared equal 2x minus 3. What should we do to solve that? Add x squared. Please stop trying to factor when you have minus x squared. If you have a negative a value, it is so much harder to get your factors correct. Not saying it's impossible, but it is a lot harder to get your factors with the correct signs if you have minus x squared. Be super careful, or just add everything to the other side. Because this is something we can solve. How can I solve this? Factor. Our a value is 1, so we can take our shortcut in factoring. We need to multiply to make -3, add to make +2. -3 and +1 will not multiply to make, or will not add to make a +2. -1 and +3 will multiply to make that -3 and add to be +2. So our factored form is our x with that +3, x with that -1 to get our factored form. So what are our roots or our solutions? -3, +1. And if I go and substitute either one of those in, e to the negative, parentheses, -3 squared, I will get the same values if I do e to the -3rd and then square it times 1 over e cubed. I'll get the same value. It's not going to be pleasant, but I can do it. Same thing with e to the 1st. I could substitute 1 in place of x, and I could check it if you really want to. If you're not sure if you did it right, it's a great way to double check. Questions on this one? Because these are our solutions. One more like this. Because sometimes we get really icky looking ones. Like 4 to the x times 1/2 to the 3 minus 2x equals 8 times 2 to the 2x. What should we do? How in the world are we going to approach this? Say it again. All of these can have a base of 2. I need them all to have the same base. We do not have tools for doing this without the same base. So between a 4, a 1/2, an 8, and a 2, those are all multiples of 2. I can work with that. So we need to switch everybody to have a base of 2. So when I rewrite 4 to the x as 2 squared to the x, and I can rewrite my 1/2 as 2 to the -1, and it's got that same power, 3 minus 2x. What about 8? 2 cubed, 2 to the 3rd. And then the last piece is already a 2, so I don't got to worry about that guy right now. 2x. So I'm going to do a little simplifying on the left-hand side here because we've got our 2 squared to the x. That's 2 to the 2x. We multiply our exponents together. And here we're going to have 2 to the -3 plus 2x. When I multiply -1 times 3 minus 2x. If you want to put that as 2x minus 3, that is also valid. Because the whole point is I want to be able to combine these together. I want to be able to get 2 to the something equals 2 to the something. Because then I can just look at my exponents. Whenever we are multiplying our bases, what do we do with our exponents? Add them. So this side's going to be 2 to the 2x plus 2x minus 3. And this side equals 2 to the 3 plus 2x. So we have to add on both sides, looking at these exponents. Now that I've gotten them down to the same base with exponents, I can look at just my exponents. While we do that, I'm also going to simplify this side again so that we get 4x minus 3 equals 3 plus 2x. Now that we have those bases the same, I can look at just my exponents. What can I do from here? More specific. Subtract 2x on both sides, add 3 on both sides. Absolutely valid. So if I subtract 2x on both sides, I get 2x. If I add 3 to both sides, we get 6. So what does x equal? 3. And again, I could go back to the very, very beginning. Substitute in 3 in place of every single x. 8 times 2 to the power of 2 times 3. 4 to the third times 1/2 to the 3 minus 2 times 3. I will get the same answer. It will be a big number. I could do it. Don't need to, but I could. So if you're not sure if you've done it right, substitute it back in. Totally valid. Okay. Yes, sir. Yes, sir.
Just multiply the way we were beginning, like the 4 and 1/2 and 8 and 2.
Because they have the different exponents on them, we can't just multiply the bases at the beginning. Because it's exponent rules make things fun. So they have to be the same bases in order for us to be able to do that. Yes. Okay. We had 2 last story problems to finish out, and then we're going to finish out sections 5.2 and 5.3 today. So, because they all kind of do very similar things. So we had 2 last story problems. If you do not have a copy of that, I have a few more if you'd like them. It was the bottom 2 on the big list. Does anybody need a copy of them or want a copy of them? Yeah, go ahead. So we're going to be using these to kind of solve. Our most important set of words up here says compounded continuously. That lets us know which formula we're going to use. So whenever we see this continuously stuff, that means we are looking at PERT. A equals PE to the RT. Whenever we're compounding continuously. So if we have $100 deposited into a savings account that gives interest at 3.5%, how much is going to be in the account after 10 years? So what pieces do we know to fill into our PERT equation? What's our principal? I heard we know that. 100. So $100, that's our principal. So we have our 100. E is a number on our calculator. What else do we know? Our rate. What's our rate? 0.035. 3.5% per 100. 3.5 divided by 100 gives us our decimal, 0.035. What else? Got our rate. One more piece we need. Time. 10. Times 10. That is all going to equal the amount that's in our account. So, how much money will be in our account after 10 years? $141.91. Which is not very much after 10 years for it to grow. But it's free money. Free money is free money. Whenever we have money, we're going to round to 2 decimal places. And call it good. If it's ever living creatures, whole numbers only. Questions on this one? That's as far as we go on it. Ta-da. The next one is giving us slightly different information, but it's using the same equation. So this one, we are doing what principal would you need if you wanted to have $15,000 in 4 years? So you know you want to buy the new smart truck that they're releasing in 4 years. So they've given you the, my husband does this all the time with the dream cars. Makes a list and he's like, I would love to have this car. If we did this, I would need this much in savings right now. Actually, he comes to me, how much will I need in savings if I want to have this car? So it's a slightly different information that they're giving us. We're still working on compounding continuously here. here. So we're still going to have the amount in our account, or the amount that we owe, is our principal, e to the RT. But we know different pieces this time. What do we know? We know A. A is the amount that we want to have. That is usually our answer. How much is our A? The 15,000. I want to have 15,000. I need to know what I need to put in my savings account so I can walk away and come back to $15,000. So our $15,000, we are asked to find P, so that's what we don't know. That letter's still going to be there. E is a button on our calculator anyway. It's just a number. What else we got? Our rate. What's our rate? 0.045. Okay, one more thing we know. 4 years. We know our time. So times 4. How could I figure out what P needs to be? Divide by that. I can either divide by E and put it in the calculator as a fraction that has the E, or I can switch the E to be a decimal and divide by that. Either way. So I'm going to write it both ways just so we can see it. I can either do my 15,000 divided by E to the 0.045 times 4 and put it in the calculator like that. Or I could take and do my 15,000 equals my principal times whatever we get when we take our E to the power of those numbers, and we get 1.19722-ish. 217363, blah, blah, blah. And then I could divide by the number. So either way, I can find my P either by putting it in the calculator like this with the exponent, totally valid, or switching it to decimal and then dividing both sides by it, also valid. What do we get as our principal? How much will we need to put in? $12,529.05. So if I know that in 4 years I need $15,000, if I've got 12 grand, I'm set. I can get $2,500 free dollars just by letting the bank hold on for it for 4 years. We do love a free money situation. Okay. Questions on this one? Because sometimes they give us different information than we anticipated. Okay. The last part of both section 5.2 and 5.3 is graphing, and it is done the same way, so we're doing them kind of together. So we're going to be working with graphing exponentials, and our transformation form is going to look kind of like this. A times B x minus h plus k. This b is not the 1 over b that we used when we were transforming before. This b is our base. It's not the transformation b, it's our base. So we're not really going to do b transformations where it would reflect across that y-axis so much because it's we have b meaning other things here, so we're not going to use the b transformation. B is our base. So A, H, and K have the exact same job they've always had, where A is in charge of vertically stretching or compressing. It's also in charge if we reflect over our x-axis. So this will tell us if we're right side up or upside down. Back to A in just a second. Our B is going to be our base. This will be how we find our parent function. Our parent function for any transformations will be b to the x. So exponential functions are going to have different parent functions for every different base. 2 to the x has a different parent function than 3 to the x, which has a different parent function than 1/2 to the x. They're related, they're similar trending, but they're not the exact same parent function. So it's not that we're going to use b as a transformation, it's where our parent function comes from. H is still going to have the opposite sign as normal. It still does that ha-ha opposite. And it's still going to be our horizontal shift. Horizontal. Which I spelled wrong. Horizontal shift. It's going to move things left or right. Our K is still going to be our vertical shift. It's going to move up or down. K is also going to be where our horizontal asymptote. It's going to be at y equals k. Every single time. So a lot of times when we're graphing these and we have a transformation like a k, we'll start by plotting up our asymptote. We'll put that on there. We have a couple of different ways we can go about graphing these. We can do these exactly the way we did our transformations before, where we make our parent function, we take our a and our k and our h, and we put it through our x plus h, y a plus k. 100% valid way to do this. There's also kind of shortcut ways to do this where we draw our asymptote first. Our a is about our y-intercept, how far it is from that asymptote. And h would be where that next step goes. So there's a couple of different ways to do this, and we're going to look at a couple of different sets of graphs. We are totally good on time. So on the tables, there should be some of like pairs of graphs. We're going to do probably 4 graphs hopefully today. So if you need more, let me know. I have plenty. Yeah. I was going to say there should be some out on tables, but depends on how many people left. I'm going to put a few more out. There's some on there.
Oh my gosh.
Yeah, good. So the first one we're gonna graph is 2 to the x. So if you guys need more graphs, let me know. I have more. I always have graphs up here. So if you ever need graphs, if you want to like do one homework, whatever, I have tons. Or if you ever want like a whole sheet of just graph paper, I have graphs and graph paper. Like welcome to use. Anytime you need. So the first one we're going to graph is 2 to the x. Fairly familiar. We've seen these kind of guys before. This is a parent function. It doesn't have any a transformation, h, or k. So this is just b to the x. So on these ones, more often than not, what we're going to do is we're just going to pick our 5x values, substitute them in, and find our y values. Where we want a good view of the middle, so we tend to do things like -2, -1, 0, 1, and 2. 100% totally valid approach. We could substitute that in. 2 to the power of -2. Well, 2 to the power of -2 is 1 over 2 squared, or 1/4. 2 to the power of -1, that's 1 over 2 to the first, or 1 over 2. 2 to the 0 is 1. 2 to the first is 2. And 2 squared is 4.
You're so smart.
So if we plot up those points, we'll start to see what's happening. 2 to the 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. Before I connect these up, I am going to draw in my asymptote here because we do have one. Oops, not that. Our asymptote's going to happen wherever our k is. Our k at this point is 0. So we have an asymptote at y equals 0. So right on our axis. So right, making that slightly darker. So our asymptote's going to be right there. So when we connect this up, it's going to look kind of like that. There is another way you can go about trying to graph these, where it will not take a full table. It takes a little bit of slightly different thinking for our h to be happening at 0. It's up a from our asymptote, and then b happens next, so we times by b. Not a huge thing, but if you are one of those people that doesn't like to fill in the whole table, h tells us where this is going to happen. So our h is 0. We go up a. Our a is 1 here. To get to 1, 1 times 2 gives me 2 for the next one. So it's an option for how to do that. That is not something you have to do. But if you're one of those people that are like, I hate having to draw out the full table, it's an option for how to do that. So, table is fully fine, absolutely, totally fine option, but you don't have to. So when we get transformations, I'm going to show you how to do that. I'm going to do the transformation old school style first, and then I'll show you how that would look if we looked at this slightly differently. So our next one that we're going to do is a transformation on 2 to the x. So we're going to use this as our parent function for the next one. So we're going to graph minus 2 to the x minus 1 plus 3. And we're going to do this full graph. So we still have a base of 2 on this. So we can use the parent function we just made our table for to do this old school, where we pick our x's, find our y's, and do a transformation that way. Our transformation will be based off of that same parent table we just wrote. So I'm just going to rewrite that over here. If you want to rewrite that, totally cool. If you don't want to rewrite it, since you can see it on your page, also totally cool. So we'll just have that same exact table, our 1/4, 1/2, 1, 2, and 4. Oh, that's very small. Goodness. I zoomed in very close. And you can 100% do this the old school way, where we took and made our transformation table and applied our transformations, where we would take our x plus h, and we'd always remember how much graphing makes us yak, ya plus k. 100% valid. What is our h? 1. That guy's h right there. So I could take all my x values from my parent function and add 1. That's a thing we can do, and we will hear in just a second. I can take my y times a plus k, so my y to my parent function. What's our a? Careful. It's not 2. 2 is my base. Negative 1. In other words, a b to the x minus h plus k. So a is times in front. So our a is actually this minus out here, minus 1. What's our k? 3. So I could take all of this stuff, all of my parent function. I could even take the asymptote for my parent function where I had my y equals 0. And I can apply all these transformations to it. My x's plus 1. So negative 2 plus 1 gives me a negative 1. Negative 1 plus 1 gives me 0. 1, 2, and 3. So adding 1, 100% valid. My y's times negative 1 plus 3. So these are going to be a little bit harder. So 1/4 times negative 1, we get negative 1/4 plus 3. 2 3/4 or 2.75, 2 3/4. 1/2 times negative 1, so negative 1/2 plus 3, we get 2.5 or 2.5. Genuinely, I do not care if you do decimals or if you do fractions. On graphs, it does not matter. We are estimating anyway. So we're going to get 1 times negative 1 and then plus 3. Now we're going to stuff it's a little bit easier to do. So we've got our 2. 2 times negative 1, so negative 2 plus 3, get 1. And then we'll get a negative 1. And if we plot up these points, negative 1, 2 3/4, 0, 2.5, 1, 2, 2, 1, and 3, negative 1. We get our points that look like this. We would also need to find our asymptote. Our asymptote, we can actually do the transformation in the same way. Plug it through the y's. 0 times negative 1 and then plus 3. Our asymptote's happening at 3, wherever that k is. So our asymptote is happening, ooh, that's too chunky. Our asymptote's right here. So our sketch or our graph is gonna look like this. If we're looking at trying to do these kinds of graphs using that kind of shortcut way I kind of mentioned where we use h, our h being 1 means we're going to look where our x is 1. Our first point is going to happen a away from our asymptote. So our a was negative 1. So I go down 1 from my asymptote and we get this first point. I take that a, my 1 right there, we go times our 2. So we went down 1, and now I times my base, go down 2. And I get that next point. So you can do this as a kind of shortcut, where this moved with a, and then this is down from my asymptote, or this moves from my asymptote b times a. So off from that asymptote. So you can absolutely do this the full way this way where it takes the 2 tables, or we can do it with the transformation kind of shortcut thing. I don't care how we graph them, we just need to be able to graph them. What is our domain on this one? Negative infinity to a positive infinity. It's all real numbers. What's our range on this one? Negative infinity to 3. Do we include the 3 or we exclude the 3? Exclude the 3. I can get real close to 3. I can go like lean on the 3. But I cannot actually equal 3. Easter.
I don't get the shortcut.
I was gonna say, you don't have to use a shortcut. You don't have to use a shortcut. It's based off of where our asymptote is. So asymptote happening at K. Wherever H is, we use A to find our point. So if it was A was positive 1, we go up 1. If A is negative 1, we go down 1. So from our asymptote, we find H. We move A. So this was negative 1. Our next point is from the asymptote, B times A. It works. It's not necessarily better. It's not necessarily worse. It's just an option. And if you want to do the full table, more power to you. Just giving you an option here. The process is 100% the same, even if the base is unpleasant. Like e. E to the x. This one will probably require us to use a little bit more in the calculator, or we can use the shortcut thing. This is when the shortcut will sometimes come into help, because here we know that our base is E, which is about 2.718-ish. So if we were to make a full table, 100% okay, we can type it in the calculator. E to the minus 2, e to the minus 1, e to the 0, e to the first, e to the second. I can get points, I can line them up. Absolutely valid. I can also start with my asymptote being at K. Here our K is 0, so we're going to have an asymptote at 0. If there's nothing added on the end, that's where our asymptote is. Our A is 1. There's no number out in front, right? And our H, we don't have anything added or subtracted in my exponent. So here my H is 0, right? So I could 100% make the whole table. If you want to graph with the shortcut, here's the benefit of the shortcut. I know that where my H is 0, right here. I'm going to be A. So my A is 1, so I'm going to go up 1. So my first point's going to be right there at 0, 1. So I'm going to use A to find this first point. Up A for my asymptote. Then my next point is going to be A times B from the asymptote. It's going to be 1 to the right, and it's A times B. So 1 times 2.718. 2.718-ish. So there. This is A times B from my asymptote, is how I'm getting that. I know it's going to approach my asymptote here, and it's going to keep going that way. Absolutely 100% okay to still do a table. This also works. This would 100% count with work, like plenty, right here. Absolutely, filling out table. Without the shortcut, it is 100% still doable. Picking our x's to find our y's, and that is 100% okay. We're just going to take, when we have no h transformations, we're going to start with our parent function and go from here. So e to the x, e's button on the calculator, we're going to type them in. If I get e to the minus 2, we get about 0.14. E to the minus 1, we get about 0.37. E to the 0 is 1, because anything to a 0 power is 1. E to the first is 2.71 or 2.72. And e to the second is 7.39-ish. And this actually lines up with exactly what my first sketch shows. So our -2 being here at about 0.14, -1 about -3.7, 0, 1, 1, 2.72 up here, and 2, 7.8. If I was good at sketching, I'd be right on it. So it totally works to go that way as well. 100% okay. Showing you options. So transformations with E are 100% the same process. X plus H, YA plus K. Because graphing makes us yak. Okay? So everything in 5.1 or 5.2 and 5.3 are very much in those same kind of veins. Either solving or it's going to be graphing of some sort. And you have 2 minutes until we get to the end of the period. Cool, cool, cool.
I wouldn't be surprised because no, you said you put that in on accident because you did it for his first class. It's really taking a while to grade. I know what teachers do. They really have an outstanding assignment. How they grade it. Like they have an outstanding assignment that they
Wait, he has been in the grade. He just put it in 4 minutes ago.
Bro, 4 minutes ago.